All right, today we're going to talk about Chapter 11, which is going to deal with hypothesis tests about two population proportions. And this is 11.1. In 11.2 and 11.3, we'll also talk about hypothesis tests dealing with two samples, but those will be different than this one. This one deals with proportions. So in this one, we're going to compare two population proportions and test whether they are the same or whether they are either different or whether one is greater than or less than the other. So those will be our three choices for the alternative hypothesis. The null hypothesis will be, as always, that they are equal, the proportions from the two populations. These are independent samples, meaning that the individuals that are selected for one sample do not dictate which individuals are to be in the second sample. So these are both random samples from the populations that are being compared. A sampling method is dependent, and this comes up in the next section, when the individuals selected to be in one sample are used to determine the individuals in the second sample. These are matched pairs, and that's not what we're dealing with in 11.1, but in 11.2 we'll talk more about these matched pairs, where you have like a husband and wife pairs that are where you're comparing the husbands and the wives, a parent and a child, two siblings, and sometimes even in that one you compare an individual to themselves before and after some kind of event or treatment. And so that will come up in 11.2. But for 11.1, we're going to deal with independent samples, and we're going to compare two population proportions and test a hypothesis about those proportions. The notation is pretty much what we're familiar with. It's just that now we have two samples, so we have to use a subscript to distinguish them. So P1 is the proportion for the population 1, N1 is the size of sample 1, and X1 is the number of successes in sample 1. And P hat 1 is X1 over N1, in other words, the proportion for the first sample. Then you use a 2 for the second sample, the same symbols. P2 is the proportion for population 2, N2 is the size of sample 2, X2 is the number of successes in sample 2, and P hat 2 is this should be 2, X2 over N2. That's printed wrong, so make sure that you take note of that. All right, so samples obtained independently by simple random sampling or data come from a randomized experiment. That is essential. And you have to have the same thing we've had before, the sample size times the probability of success times the probability of not success, multiplied together has to be greater than or equal to 10 for both of the samples. And the sample size has to be no more than 5% of the population size, and that's to guarantee independence. The hypotheses then will be, the null hypothesis will be that P1 equals P2, that the two populations for the two proportions for the populations are equal. Then our alternative hypothesis will be one of these three, either that they are not equal, that P1, proportion 1, is greater than proportion 2, or that proportion 1 is less than proportion 2. So you can have any of these three depending on what it is you're trying to make what the claim is. So here the proportions, one for each group, are being compared in the test. So we're comparing them. The test statistic and the p-value will come from the calculator, and this is the test that we'll perform on the calculator under stat and then tests, and it is a 2-prop z-test. It's number 6 in the list. We are not going to draw a picture, and we're not going to worry about critical values here. We didn't earlier too much either because we weren't working it that way, but we're not going to draw the picture here at all. So just the test statistic, which the calculator gives you, and the p-value, which the calculator will give you. All right. For an example, in October of 1947, the Gallup organization surveyed 1,100 adult Americans and asked, do you totally abstain from drinking alcoholic beverages? Of the 1,100 adults surveyed, 407 said yes. In July of 2010, the same question was asked of 1,100 adult Americans, and 333 said yes. Has the proportion of adult Americans who totally abstain from alcohol, has it changed? Use 0.05 significance level. So that is our alpha. All right. The null hypothesis is that they are the same, that proportion 1, which came from 1947, and proportion 2, which came from 2010, are the same. And the alternative hypothesis is that they are not equal. So remember, change doesn't, we're not trying to determine which might be larger, even if they're not the same anymore. We're just looking at, has it changed? This is a two-tailed test, and if we support the claim, which is this, we still can't say this one's bigger than that one, because that's not what we're testing. We're testing, are they different? So for 1947, we have this information. 407 said yes out of 1,100 people, and the proportion for that is 407 over 1,100, which is 0.37. In 2010, we had 333 yeses out of 1,100, and so that proportion is 0.30. So the calculator will give you this as well if you need it. The test statistic is 3.34. It is a z-score. We filled in alpha, which was given in the problem as 0.05. And then when we perform this on the calculator, because remember we're doing a two-prop z-test. So we've got stat, tests, this is number 6, so it's down here, and we put in the information from here. So x1 is going to be 407, 1,100 for n1, x2 is 333 out of 1,100 also, and they don't have to be the same size. These happen to be, but they don't have to be. This is a not equal to that we're testing, so we choose that one, and we go down and calculate, and it gives us the z-score, which is where we get this 3.34 from here when we round off to 2 places. The probability, the p-value is 8.4 times 10 to the negative 4. Remember, this is scientific notation, which if you write it out is 0.0008, which is very small. It is a lot smaller than our alpha, which is 0.05. So p is low, so we reject H naught. And when we reject H naught, the conclusion is there is sufficient evidence to support the claim that the proportion of American adults who abstain from alcohol has changed. And again, regardless of what the proportion is, we can't say, oh, it went down, because that's not what we were testing for. We were testing for, has it changed? Obviously, if it's changed, it'll be lower or higher one way or the other. If it was exactly the same, we wouldn't be testing, has it changed? But we did not test for, has it gone up or down? We just tested for, did it change? So that's what we can conclude here. In the next example here, we have, in a study of red and green color blindness, 500 men and 2,100 women were randomly selected. So like I said, these are being compared to each other as long as the samples are large enough. They don't have to be the same size. Among the men, 45 demonstrated color blindness, and among the women, 6 demonstrated color blindness. Is there sufficient evidence that alpha equals 0.05 to support the claim that men have a higher rate of red-green color blindness than women? And again, that's a proportion. Make sure that you keep track of which one you're assigning to 1, the P1 and the P2, writing it down like this, where you write the name of the group and then number 1 and number 2 can really help, because sometimes you accidentally get them backwards from what you think you have, and then you're testing it the wrong direction. All right, so our null hypothesis is that P1 equals P2. P1 is the men, and we're looking for a higher proportion of men having color blindness. So we're looking, our claim is that P1 is greater than P2. The proportion of men who are colorblind is greater than the proportion of women who are colorblind. So our alpha is 0.05, as it said in the problem. Our test statistic we're going to get from the calculator, and again, we have all of these things to put in, so we're going to do the same test we just did. Stat, test, 6, and x1 is 45 out of 500, x2 is 6 out of 2,100. You can kind of see where this is headed. And we're looking for greater, because we're looking for P1 to be greater than P2. And again, we're not looking at raw numbers, we're looking at the proportion formed by these two numbers. So we go down here, and this is a right tail test. And then we're going to calculate that. And you can see here that our test statistic is z equals 12.63 when we round off to 2 places. And our p-value is 7.6 times 10 to the negative 37. 10 to the negative 37. So if we were to write that out, there would be 36 zeros in front of this 7 before we got to where the decimal point goes. So basically that's 0. Sometimes it's so small the calculator actually just says 0. But sometimes it actually gives us this, but remember, this is an extremely small number. So P is very low. We reject H naught. And our conclusion when we reject H naught, remember, is that there is sufficient evidence to support the claim that men have a higher rate of red-green color blindness than women. So our claim was that men have more color blindness, have a higher rate of color blindness, and that is what's supported by this evidence. All right.